welcome everyone to Practical 5, which is session 11. And as usual, I'll just allow you to ask questions. And then, if we didn't have any questions or had time left, then I would go through the practical itself if I see something that is particularly challenging or important and so on. So feel free to ask any questions. And you can take a couple of minutes to look at the solutions, which should be both Moodle and on my website. I mean, the structure is very similar to the last practical. So first of all, we look at this synthetic data, and we note that this quasi-likelihood model will essentially give you the same sort of answers, except for the fact that the variability will have been blown up by the estimate of the dispersion parameter that the quasi-likelihood model allows for, right? So the estimates are of course the same because we are finding the zero of the same function, which is the quasi-likelihood, quasi-score function. And it should be clear that because in the quasi-likelihood models we don't make any distributional assumptions, then the AIC cannot be computed. And then in terms of coverage, one can check. So there is this piece of code here, and one can check that the coverage is definitely a lot better than it was in the Poisson model, which was too restrictive. Any questions about this synthetic data?
Why is it that the feedback gives you AIC not applicable? Why does it just not mention that the AIC is there if it doesn't make sense to ask for it?
Yeah, I mean, I guess it's just that the GLM, I mean, we're calling the GLM function that generally speaking would always return the AIC. And so rather than deleting it, I guess if you think of it, from a programming point of view, then the AIC is just an entry, right? So you want to give it a value and still print exactly the same thing for all of the possibilities of a family argument. So I think it's more of a programming, sort of detail.
Okay.
Yeah. Hi. So, is it immediately obvious why the ratio of the standard errors would be the square root of the?
It should be from. So okay. So the let me just show you. Let's see.
I mean, are you just thinking of this as sort of you just take the original model, but then just say it has larger variance and don't worry too hard about what the distribution is?
Well, let me show you. So, so we have this data that we produced, then we fit the model, and then so the estimates are computed through finding the zeros, right? So that should be clear. And then how does one compute the standard errors? Well, these are computed from the asymptotic results that we used to have, right? So, it could be theorem 1 or theorem 2 in case of the usual GLMs. But for quasi-likelihood, and in this case, quasi-Poisson, what one uses is the asymptotic result that I gave in the theory session yesterday in the recording. And in that one, I was saying that, if you have the if the assumptions of the quasi-likelihood model are satisfied, which are the expectation and the variance assumptions, then one gets as the limiting variance exactly the same as in theorem 1, right? So the large sample asymptotics of the GLMs. And from that one, you can see in the W matrix, I seem to remember, that the variances will be multiplied by the new dispersion parameter, the one sort of allows for in the variance assumption, new variance assumption in the quasi-likelihood model. So there is a comment there, and there is a comment as well in the theory. So that's where it's coming from, basically. And so this is really, it has been built. I guess what I want to stress here is that it has been built taking that into account. So it should be exactly the square root of the parameter.
Yes, okay, I see. Thanks.
Yeah. And this is a very useful construction, generally speaking, because you just do your usual GLM, and if the only difference that you have in the in your GLM and the quasi GLM is this dispersion parameter, then it's just a matter of computing that generalized Pearson statistic.
Does it make sense to talk about something that kind of looks like a Poisson distribution but has like twice as much variance or so? Because I can sort of imagine what that would look like, but then I maybe struggle to imagine what it would look like to have a Poisson distribution with 100 times as much variance. I mean, do these?
Yes, I mean, we're not really assuming anything in terms of likelihood, so we're leaving that completely undefined in some sense, as in the shape is not. It's not something we're really concerned with in this case. I don't know if that answers the question. So what exactly is the question? Like you just want to imagine the distribution?
Well, I'm just trying to get a sense of what we're actually modeling it as might look like.
Yeah, I guess it's just fatter tails.
Yeah, okay.
Fatter tails with a similar mean, if you can do that, which is it would require a bit of fine tuning, I guess, in the plot.
Yeah. Yeah, I have a question about the coverage there. Mm-hmm. So when we have just the plain Poisson model taking into account both X and Z, of course, that's like in some sense the correct model. So the coverage is like very, very good. Well, as in like it's as close to 95% as you would expect. And of course, when you have a model missing one of the covariates, the model is sort of like badly specified, or like it's the data is sort of over dispersed, and you don't see the right amount of coverage. And then you're sort of saying that in this like better model, or like not necessarily better model, but like model that allows you to account for over dispersion sort of explicitly, it can sort of understand that it has that extra degree of freedom which allows it to model the dispersion properly, which then gives it better coverage. It like how good is like good? Because I mean, the old one had like 73% coverage or something, and this one has like 92%. I mean, it doesn't necessarily seem obvious that that's much better.
What, 92 than 73?
Well, I mean, it's obviously closer, but like, you know, is it a general feature that these like models that can account for over dispersion are like a lot more accurate, or is that sort of a feature of this particular example?
No, so I think it's a more general feature. So I guess the key here is that with the Poisson model with just one covariate, you have completely specified everything about the data distribution. You know, so you have no freedom to account for anything else than what you've given it. While here, you know, you haven't really fixed much other than the mean and the variance, right? And so this will, of course, be able to adapt a lot better to things that you haven't really accounted for. And then regarding the actual coverage, you sort of need, I mean, you need the two assumptions of a quasi likelihood model to be satisfied for the coverage to be correct. So certainly that is an assumption, and this is because of what I was saying of this large sample asymptotics. I mean, the large sample asymptotics, they assume that you have, you know, that your mean and variance assumptions are correct. But now the mean and variance assumption, you know, if the mean assumption is correct, then the variance one is not so difficult to be satisfied in some sense, because all you're saying is, you know, all you're saying is that somehow you can split this influence, right, into the mean that you're modeling first times, you know, a parameter. And if you think of the data that is being produced here, then indeed that is exactly satisfied in this case, because you can have this phi, because you have the exponential, then indeed you can have a product of things and it will be approximately satisfied. And so, yes, so I guess the answer is quasi-likelihood will be a lot more flexible, and so you will generally be trusting it a lot more. But then also, yes, it is linked to this example, because this example actually gives you the assumption being satisfied approximately.
Yeah, I suppose I can see you're sort of actually almost explicitly constructing a model which does this by adding the Z in.
I mean, you could have made a different assumption, but it's true that quasi-likelihood will generally say, well, let's have a product of, you know, this new dispersion parameter and the mean.
I have a more boring question, which is, in this R code, sometimes when you call the GLM function, you say family equals Poisson or quasi-Poisson, say, and sometimes you have that in quotes. Is there like a difference, or is that just the syntax is just kind of arbitrary? Or
yeah, there's no difference. I think what you have as a difference is that in these, so if you want to specify the link function and the variance function, so the link would be applicable to both GLM and quasi-likelihood, and then the variance is applicable to the quasi-likelihood, so you could change the variance function. Yes. Then in that case, you shouldn't be using quotation marks, because this will in itself allow you to change, so as in you could do in this family, if you had quasi, then here you could write the link. You see the hint here?
Oh yeah, okay.
So you could specify certain sort of parameters, while if you had quasi written as this, then you wouldn't.
Yeah.
But other than that, I mean, if you're talking about Poisson and you're not interested in changing the canonical link, then it doesn't matter whether you write it within quotation marks or not.
Yeah, okay, thanks. Yeah.
Okay, should we move on to the self-harm data? So again, just take a look and ask any questions. I mean, I think this one is just pretty much the same as the previous one.
So just looking at how this has been done here, you're sort of saying that it's equivalent to fit a Poisson model, but then just like get a summary as if it were an over dispersed Poisson model or quasi Poisson model. Like the fact that it's a quasi Poisson model doesn't affect the actual like linear modeling, or
yeah, the mean you're modeling it in the same way, right? Because you have this link function that you need to choose, and if you don't specify it, then it will take the canonical one for the sort of family that it is trying to replicate.
And yeah, I suppose the extra variance has no effect on any of the like parameter estimation.
Yeah, because in the quasi-score function, it just, because you're equating that to 0, then it just vanishes.
Yes, I see.
So I have a couple of questions here in the chat. I'm not quite sure I understand why we have T. Okay, so I will answer to Benjamin, and then okay. Thank you, Lenny. Yeah, so Benjamin, so yeah, just so why is it a t-test? Well, it's simply because so when we have the Poisson family, there is no over-dispersion parameter. So in the standard errors, we don't need to normalize by anything, and so you get basically the usual asymptotic normality of the parameters, the parameter estimates. And however, in quasi-Poisson, we are allowing for this dispersion parameter, which under certain assumptions should be distributed as a chi-squared distribution. And so if you take the square root and then divide your normal, then you get a t distribution rather than a z distribution. So it's just the same idea as in any GLM in which you do have a dispersion parameter. So essentially, I'm just talking about the normal linear model. I hope that makes sense. Okay, so should we go into GLMMMs? So this example is, this is showing that, I mean, on the one hand, we've got this fact that these models are not only useful to model over dispersion, but rather just dependencies in general, right? Which in some cases can give rise to over dispersion. But in the normal linear model, then we can account for any dispersion with the usual standard deviance, standard error parameter. So here we see these dependencies, which are coming from a so-called longitudinal study. And these are very, very common studies. So it's important to know these models.
Just when I was looking at all of this, it doesn't seem entirely clear as to what the advantages of taking this into account are, because very obviously looking at the data, they're sort of there's some very obvious dependencies that are arising from each measurement coming from the same person. They're sort of all approximately linear with an intercept, which is, say, you're imagining it as a random function of the random variable depending on who the person is. But what is, I can see that means that's a much better model in terms of explaining what's going on, but what are the actual benefits in terms of incorporating that into your model? What's it changing about the model? Because I mean, for example, things like, some of the parameter estimates are basically the same. It might be exactly the same. I can't remember, but
yeah. So I mean, there are certainly benefits to it. I mean, firstly, conceptually, you should always, if you know something about the data, then you should try to input it, right?
Yeah, it definitely seems like the right thing to do modeling wise, but it didn't seem to make actually that much difference.
Well, not in the estimates, but in anything that has to do with testing, it will make quite a difference. Because, now if you were to, so for instance, if you were to test this linear model versus the mixed effects linear model, then you would see that certainly you're accepting the mixed effects one much more than the other one, or you should be. And this is because, you can tell that things have been modeled much better. So I guess that would be conceptually. Now, if you go into the actual sort of details, then what do you have? I mean, on the one hand, so in testing, if you have a better model, then generally speaking, you will have a better power in the tests. And this is something that is always desirable. Then the other thing is, fine, maybe the estimates are similar, but there is a computation at the end of the example. I think it's this one and not the next example. Maybe it's the next example. Yeah, it could be just a, yeah, so it's, wait a sec. Yeah, so it is in this one here. So you could have done this computation of, so there is a question here that I ask, why do you think there is a table of correlations for fixed effects? And the reason there is that, I mean, it's not very clear at first when you see it. So you see, a table of correlations, but then what you should do is to compute the equivalent sort of not mixed models, so just with fixed effects, and then compute the matrix of correlations of the estimates. And then you will see that the correlations have been decreased massively, basically, in the new model with random effects. And this in turn means that the estimates are going to be a lot more stable to changes in the data. So, you're really, getting rid of a lot of correlations that can be very negative in terms of, certain things. So like changes in the data, basically.
Okay.
So yeah, it's probably a good exercise to check that as well in the linear model example.
I was just going to ask about the diagnostic plots. You said there's nothing to conclude that there's anything wrong, but I thought we were meant to expect that residuals and fitted values were independent of each other, and in this case, they kind of line up in lines.
Wait, can you ask again, please?
So you say to look at the diagnostic plots for the first orthonormal linear model one. And do we expect that the residuals and the fitted values are independent of each other? Because I thought you did in the linear model.
Yeah, so they should be showing no patterns, right? So we shouldn't be able to spot out any patterns. And so I think in these diagnostic plots, you cannot really pick up any such patterns. Let's see, is it, was it a bit later then? Yeah, so it is a bit later. Yeah, so I mean, in terms of dependencies in this case, it's not very clear, right? Because you have this, you have this fit that is approximately like a straight line around 0. So you have this variability, right? That would agree with a normal distribution, possibly. This one doesn't look too great around here, but it's not immediately clear that it's violating the QQ plot. And then same story here as in the first plot. So I don't know if I'm answering the question in any way. I mean, I don't see any issues with I mean, what dependencies do you see? I guess that would be the question. What dependencies do you see here that would worry
you? Sorry to be annoying, but my internet completely died for just as I asked that question. So what was the? Is there a reason we should expect in lines, vertical lines, or?
Well, the vertical lines have this interpretation that you have data points only at age 8, 9, and 10, and so on, which is of course translated here.
Okay.
But that's I mean, that is an indication in itself that the normal model, probably is not the right model. Well, actually, no, it's not, because that's just depending on a certain covariate, right? So it's just like if you were saying, let me just see. Yeah, so that's just like saying that there are different factors that are giving rise to this data, right? Which is not necessarily violating a linear model, because you could have, you could have modeled this through precisely this factor, which is the identity of the patient, right?
Yeah. Okay. Thank you.
No problem. So I guess so what would give you really information here is to try to plot precisely whether there is any relationship between data points here, and there for a given patient identity, right? Because then if you had spotted out exactly this kind of dependency here, that they're joined and they're nearly in straight lines, then certainly that would be violating the normal model. But otherwise, if you see it like this, in which case you don't have the ability to see whether there are any relationships, it could be that this one is linked to this one at the bottom, and then that one in the middle, and so on, and then that would correspond to a normal linear model, right?
Another question about these diagnostic plots in general. For the first one, the residuals versus fitted, the one you have up, do we expect constant variance here or not? Because they're not standardized, right? So if they kind of trended up and down, but the mean was still 0, is that a violation of that diagnostic plot or not?
Do you mean? Okay, so I mean, certainly, one thing that you want to check here is this variance. So you shouldn't be standardizing here. So or you can, but anyway, what you want to check is that the variances, the spread of the data as you move across the fitted values doesn't change a lot. And that's what we see here. While what you're mentioning, I guess, is more like a tunneling effect or the opposite. Is that right?
Yeah. So do we expect the variance to be constant here? Because I thought you didn't expect it to be constant unless you standardized the residuals, because they have non-constant variance in general, right?
For the linear model, they should do. Right.
But then you have the I minus P kind of projection.
R minus P.
I mean I minus P, because for the standardized ones you divide by the square root of 1 minus PII, right? And I thought that was the point.
Right.
In
that. Yeah, but that's for that's for the following plots, right?
Yeah, there's another one with standardized residuals, and I was just wondering what the difference is then. I think it's the third one.
Yeah, exactly. It's the third one. Well, in the third one, you're really trying to, yes. So I mean, there is a difference in that here you have these raw residuals. At least when you're looking at the normal model, the linear normal model. Yeah, we need to check that again, because actually that is a question I left unanswered, I believe. I just realized as to whether they are being divided here, whether they're being standardized or not, actually. Yeah, I completely forgot about that one. Just write it down. Okay, so I'll answer that, because it's essentially the same question that I got, I think, in one of the first or second practicals.
Okay. Thank you.
No problem.
I have a question about the test for Chi2.
Which one? Sorry.
The test for Chi2, like the likely ratio test, and why the Chi2 is not appropriate.
Yeah. Okay.
Yeah. Then first of all, why it's not appropriate is because of the fact that it's on the boundary, right?
Yeah. I mean, I presume I just need to find which one you're talking.
Yeah, it's here.
I guess this one here, right? This table here.
Yeah.
Okay.
So I think is it because it's in the hypothesis of the Weeks theorem that it doesn't work? Yeah.
So I mean, it's on the it's on the boundary of the parameter space. So then that's generally you cannot expect that you get the usual limiting distributions.
Okay. I don't get why the bootstrap resolves it.
Why?
Why is the bootstrap a solution to test whether the distribution is right or not? I don't get it.
Well, I think so. The bootstrap is not really specifying any distribution, right? So what it is doing is just sampling data so that you get an idea of the distribution through the empirical distribution. And so if that's what you've got this empirical distribution, then really, you're making no assumptions of whether there is a chi-squared or a mixture of a Dirac and chi. And so, you basically take that empirical distribution as a given, as, an approximation to the actual distribution that you don't know about. And then you compare your, your output or your statistic value here to that, as if it were the true distribution, right? So
okay.
This is a bit, yeah. So I mean, if you look at the theory, and that's pretty much what this is saying.
Yeah, and what should we expect if the distribution Chi2 was right? What should we expect as a result?
If it were correct that you have the usual limiting distribution, then Bootstrap should not suffer from any issues. So Bootstrap doesn't mind whether you know the distribution or not. It just finds an approximation, an empirical approximation, and then uses that. And so it is irrespective of whether you have this parameter in the boundary of a parameter space. So that's one of the positives, is that you don't need to know whether the assumptions are satisfied or not to get the usual asymptotic normality results.
Okay, and so the final sum should be like near to 0 or near to the total?
Well, I mean, so this sum, what we're checking here in the sum is the values of the zeros that you got in this statistic, right? And so in some sense, what this is looking for is the weight of the Dirac delta in the limit. So yes, in here, just in the very last line, we are, we know from the previous cases that this is probably, the limiting distribution is probably a combination of Dirac delta and the chi-squared on 1 degree of freedom. And so this is just really looking at whether you do get zeros, that would correspond to the chi-squared, sorry, to the Dirac delta bit.
Okay, so we'll have, okay.
So yeah, so here we do use that sort of knowledge, but not really to do the Bootstrap at all, right? So here is just checking that it corresponds to what you expect. Yeah.
Yeah, thanks.
Hi, I've got a question. When we fit using MLE and when we fit using REML, I think in your lectures you said you wouldn't expect the coefficients to be the same.
Yeah, okay, they can change, but yeah, here they don't, yes.
Is there a kind of reason why they don't change here? Is it just like a fluke of the matrix, or?
Yeah, I think it's just because the sigma squared and the variance and covariance parameters not changing a lot, so then they don't give rise to very significant changes in the parameters estimates. But you cannot expect them to be always the same, right?
Yeah, sure. And I had one other question, which was when we fit I think we fit a random intercept and a random slope later on.
Mm-hmm.
And so we're estimating a matrix kind of sigma of the variance of the random effect, the covariance of the random effects.
Mm-hmm.
And I think oh yes, exactly here. And it estimates the row, the kind of correlation to be -1.
Mm-hmm.
I was wondering, is there a reason why it's exactly -1? Because that doesn't seem like a fluke.
Yeah, I haven't really thought about that. You may be able to get some intuition as to why that's happening. Let's see. Just think. So the model then is something is not liking something. Okay, but I guess what we are fitting is this bit in here. I don't have an immediate answer though. Does it worry you for any reason, or is it just pure curiosity?
Yeah, more curiosity, but I guess I feel like there probably is a reason somewhere, why it's exactly -1.
Yeah, I'm sure. This is so. I guess Yeah, so it may be, yeah, exactly. So I think what that is saying is that you shouldn't be taking a model with a random slope. I think that's what it means. And that's because, well, is that right? Wait a sec.
I guess it feels like the random slope isn't adding anything extra if you know it's like completely.
That's what I'm thinking. Yes, that's what I'm thinking, because what that is doing is saying you're always going to add exactly the same value. Given a patient, you're always going to be adding the same value, and so there is no point in having a random slope. I think that's the meaning, basically. But that must be very particular to this data set.
I was thinking maybe it didn't have enough parameters, didn't have too many parameters or something.
Yeah, or just basically you don't need this random slope because there isn't any evidence to think that that is a good modeling assumption. I mean, to be perfectly honest, for this example, I did inherit it from the previous lecturer, so it could be that he created this artificially, and so in that case, it would make sense, right?
Yeah, makes sense. Thanks.
I think you should make sure I get this straight. This is just using SDA part 1. So sorry, Benjamin, I missed your question till now. So this is really using large sample asymptotics rather than small dispersion asymptotics. So if you look at the theory, it's not even theory, but just a claim that I made at the end of the quasi-likelihood about the convergence, then that was talking about n going to infinity. That's large sample. But it would be part, what do we have there? So it would be, yeah, okay, I see what you mean now. Okay, I see why you're now talking about SDA. Yeah, remember that. So this, okay, so there is a difference between finite sample and sort of large sample or asymptotically infinite sample, in that the t distribution in the denominator will eventually converge to its mean, which is 1, and so it vanishes if you look at the exact limit, right? And this is why in the large sample asymptotic theorem you don't have the t distribution, but rather just a normal distribution. Now, if you're looking at finite samples, and in finite samples, it's probably a better approximation is probably given by the t distribution, and this of course comes from the fact that we're dividing this normal by square root chi-squared. But you're free to use both the t or the normal, really, because after all, I mean, they're both approximations, right? But probably for finite sample, it's best to use t, just from the intuition that the chi-squared will be a bit random around the value 1, basically. So I guess the short answer is that it's not really using either of them, neither large sample nor SDA. But large sample is the limit of what we're using here. And SDA also coincides with that. Okay.
I had a question.
Mm-hmm.
What is meant by that the two models are only formally nested?
Yeah. So I mean, we have nestedness. One has to be part of the other one, right? And if one corresponds to sigma squared equal to 0, when your model only allows for sigma squared greater than 0, then they're not strictly speaking nested, but they are formally in the sense of, with the meaning of formal that we have in mathematics, which is informal. I don't know if you're a mathematician, but if you're not, I'm sure that can be extremely confusing. Did that make sense as an answer?
Yeah, thank you.
Okay. Okay. Any more questions? So, I mean, no one asked about why is it that, let me see, so I think it's here. Yeah. So there is a comment here that you're probably, more than one person is probably going to be wondering about once you digest the practical, which is that in the standard deviation, we took the value coming from the fit of the alternative model, and this would have been the same as taking the standard deviation from the fit for the null model. And so this is a subtlety that I mentioned in the theory notes. I didn't mention it in the recording just because it's sometimes too sort of complicated to explain it in words, and rather it's just easier to see it in practice as you see here. And the reasoning is what I say in the theory notes, and this is that what we are testing really is the null versus the alternative under the assumption of the null being correct, right? And so if the null is correct, it doesn't really matter whether we're looking at the fit of the alternative or the fit of the null, because the alternative really should be, as you get more and more data, you should be recovering the values of the null fit. And so this is why it doesn't matter in terms of testing the null, okay? Of course it matters in other respects, but not in that sense, yeah. Let me see. So I've already spoken about this correlations, and the ANOVA. I think the answer to this is clear from all that we've been discussing so far. So if there are no further questions, then we'll close here the practical. Okay, then. So I'll see you on Wednesday for a theory lecture in which we're going to start with classification now. So we're done with regression in that, and I think conceptually maybe I should do a little summary here. But conceptually, I think it makes sense that we're done with we've covered some significant grounds in that. If you did undergrad, doing statistical modeling, for instance, then, or a course like that in which you were seeing GLMs, then these GLMs can be quite useful for proving, results in mathematics, and they are, a good generalization of the linear model. but then they have certain restrictions or they imply certain limitations like over dispersion. And what we've seen is basically, a few models that for some particular cases, they are generalizations that can account for this. And then in other cases, they're just more general models like the mixed models, mixed effect models. And we ended, so generally speaking, what we've done is parametric modeling, except for the case in which we have the quasi likelihood models. And this is why I put it last in the notes, because there we don't really make any distributional assumptions other than the moment conditions. And even with that one, we still recover the asymptotic results from GLMs under sufficient assumptions. Okay, so we'll start then with classification on Wednesday. Thank you for your attention.